In this video, we will take a look at Segre plots, which can give an insight into why and how different nuclides decay. We will then examine the spectra of alpha, beta, and gamma decays to see how they provide evidence for discrete nuclear energy levels and the existence of the neutrino. Recall that a nucleus consists of positively charged protons and electrically neutral neutrons, collectively known as nucleons. The protons will electrically repel each other, attempting to push each other away. However, when the protons and neutrons are sufficiently close together, the attractive strong nuclear force will take effect, and this holds the nucleons together. So a stable nucleus is one where the longer-range repulsive electric forces are balanced by the very short-range attractive strong nuclear forces. As more protons are added to the nucleus, they will all repel each other due to the electric force. But protons can only attract their immediate neighbours due to the short range of the strong nuclear force. So this will increase the tendency for the nucleus to break apart. Meanwhile, adding more neutrons to the nucleus will contribute to the attractive forces, and not contribute to the repulsive forces, which is why stable large nuclei will tend to have more neutrons than protons. Now let's consider the following grid of neutron number against proton number. At this scale, each vertical step represents one neutron and each horizontal step represents one proton. We will first establish how the main types of decay will appear on this grid. An unstable nucleus can undergo alpha decay, which results in the loss of 2 protons and 2 neutrons from the parent nucleus, and the emission of an alpha particle. Such a decay will cause the nuclide to move diagonally downwards 2 squares left and 2 squares down. When beta-negative decay occurs, a neutron converts into a proton, an electron is emitted along with an antineutrino. This reduces the neutron number by 1 and increases the proton number by 1. So on our plot, this decay results in the nuclide moving diagonally downwards 1 square right and 1 square down. Conversely, in beta-positive decay, a proton converts into a neutron, emitting a positron along with a neutrino. This increases the neutron number by 1 and decreases the proton number by 1. Therefore, this decay causes the nuclide to move diagonally upwards 1 square left and 1 square up. If we add the following small stable nuclei onto the grid, we get a close-up of a chart known as a Segre plot. Moreover, this plot shows that stable nuclei are confined to a very small range known as the zone of stability. For small nucleon numbers, this zone occurs when the number of protons and neutrons are roughly equal to one another. The Segre plot can also be used as a qualitative way to predict the mechanism of decay for each nuclide. When a nuclide is located to the left of the zone of stability, it would have excess neutrons. Such nuclides will have a tendency to reduce the neutron-to-proton ratio to align it more closely with the zone of stability. To do this, it would go through beta-negative decay as the neutron is converted to a proton. And as we saw, this decay causes the nuclide to move diagonally downwards to the right, bringing it closer towards the zone of stability. Nuclides located to the right of the zone of stability will have excess protons and too much nuclear repulsion. These nuclides will have a tendency to decay through beta-positive decay or electron capture, where the nucleus captures an electron and changes a proton into a neutron. Such a decay will cause the nuclide to move diagonally upwards to the left, again bringing it closer towards the zone of stability. After zooming out to the full version of the Segre plot, it shows a clear pattern where a zone of stability can be established. More importantly, if a line of neutron number equal to proton number is plotted, we see that a ratio of neutrons to protons in the nucleus gives a rough guide for the stability of nuclides. For nuclides with a proton number less than 20, stable nuclides will have roughly equal neutron and proton numbers. However, for larger nuclides with proton numbers larger than 20, stable nuclides will have an increasing ratio of neutrons to protons up to a value of 1.6. Recall that this is because for larger nuclei, more neutrons are required to provide attractive strong nuclear force to stabilize the nucleus. The Segre plot also highlights where unstable nuclides are typically found. As we showed earlier, nuclides that have excess neutrons and too few protons will be located to the left of the zone of stability and will tend to undergo beta-negative decay. Similarly, nuclides that are lacking neutrons will fall to the right of the zone of stability and will typically undergo beta-positive decay. Furthermore, this region to the upper right end of the Segre plot, with proton numbers larger than 82, contains heavy nuclides that will tend to undergo alpha decay. In these larger nuclides, some nucleons will have a large enough separation between each other where the strong nuclear force becomes less significant, and so the strong nuclear force will not be able to hold against the repulsive electrostatic force. By emitting an alpha particle, this would reduce the overall mass and size of the nucleus and increase the neutron-to-proton ratio. And as we saw, the nuclide would move diagonally downwards to the left on the Segre plot, which brings these larger nuclei closer towards the zone of stability. Recall that the emission of photons with discrete energies during energy level transitions of electrons provided evidence for discrete energy levels for the electron shells. In a similar fashion, the energies of alpha particles and gamma rays emitted during radioactive decay provided an insight to the energy levels inside a nucleus. When a radioactive parent nucleus emits an alpha particle, it can result in a stable daughter nucleus. However, what often happens is that the emission of an alpha particle leaves the daughter nucleus in an excited state. To return to the stable ground state energy level, the daughter nucleus must then emit one or more gamma ray photons, thereby giving up the excess energy in the form of electromagnetic radiation. So let's take a look at the possible decay routes of americium-241. Nuclei of americium-241 will emit alpha particles when decaying to nuclei of neptunium-237. In one decay route, americium emits an alpha particle with 5.545 MeV of energy, which leaves the daughter nucleus of neptunium-237 in its ground state. In the second decay route, the alpha particle is ejected with 5.486 MeV of energy, and this leaves the nucleus of neptunium-237 in an excited state as it has an excess of energy. To release this energy, a gamma ray photon is emitted with 0.059 MeVs, which is exactly equal to the difference in energy between the two energy levels, and then neptunium-237 will have reached its stable ground state. In the third decay route, the alpha particle is ejected with 5.443 MeVs of energy, and this again leaves the nucleus of neptunium-237 in an excited state. From this, the daughter nucleus can decay to the ground state directly by emitting a single gamma ray photon of 0.102 MeVs, or by emitting two separate gamma ray photons of energy 0.043 MeVs and 0.059 MeVs when transitioning to lower energy levels. These emitted energies can be summarized by their respective spectra, which also detail the relative probabilities of these decays occurring. Notice how the alpha particles and gamma ray photons can only have one of a number of possible energies. This means that these energies are discrete and the spectra are not continuous. The discrete energies of emitted alpha particles and gamma ray photons both provide evidence for discrete energy levels within the nucleus. If we now consider the spectra of beta particle energies, experiments showed that emitted beta particles from a radioactive nuclide have a continuous energy spectrum. This means that the emitted beta particles, which are electrons, can have a range of energies. This is in complete contrast to the spectra from alpha particles and gamma ray photons that we just discussed, which have the same discrete energies from a particular radioactive nuclide. This was puzzling for physicists at the time, as it appeared that the emission of electrons would violate the laws of conservation of momentum and energy. To solve this, the existence of a third particle being emitted during beta decay was proposed. If we consider a decay of cobalt-60 and assume a third particle is involved, we can account for the variation of energy observed in the electrons. The initial momentum of the nuclide is zero, and so through the law of conservation of momentum, we expect the total final momentum of the system to be zero. Without the third particle, the electron and daughter nuclide would be expected to move in opposite directions. With the same energy released in the decay each time, we would expect the energy of the electron to be the same for every decay. With the presence of a third particle, however, the beta particle will instead travel at an angle. With each decay, this angle will differ, and the result of this is that the energy distribution between the three particles will differ each time. This leads to the continuous distribution of beta particle energies. The third particle was proposed by Pauli and called the neutrino. Through experiments, this third particle in beta-negative decay was confirmed as the electron antineutrino, which is the antiparticle of a neutrino. Similarly, in beta-positive decay, when a proton is converted into a neutron and emits a positron, an electron neutrino also has to be emitted in order to conserve momentum and energy. We will now provide a final summary of the key understandings from this video. We found that Segre plots provided an insight into how different nuclides decayed, depending on where the nuclide was located on the plot. They also showed that the stability of a nuclide depends on the ratio of neutrons to protons in its nucleus, where this value can range from 1 to 1.6 depending on the proton number. We saw that alpha particles and gamma-ray photons emitted from radioactive nuclides can only have specific discrete energies, and this is only possible if nuclei had discrete energy levels. On the other hand, beta particles emitted from radioactive nuclides had a continuous range of possible energies, and this could only be explained by the emission of another particle alongside the beta particle, namely a neutrino or antineutrino. This now concludes our video on nuclear stability and spectra of radioactive decay. Thank you for watching.